Hello, my name is Drew and I work for Ventana Microsystems. My colleague Sunil and I have jointly prepared this power management presentation and the demos, which I'll be sharing. In this presentation, we will first review how an operating system on RISC-V gets access to platform features. Then we'll introduce ACPI power and performance states, and also what an FFH is for extending the ACPI specification. And for each state, we'll go into more detail as well as give current status of its support. Then we'll do the demos. An operating system's execution mode isn't sufficiently privileged to access platform features, then it requests software which runs at a higher privilege mode to do so on its behalf. For RISC-V operating systems, this is done with the supervisor binary interface implemented by the supervisor execution environment, which we typically say more concisely as the OS is making SPI calls. And in this diagram, we show those SPI calls. Also shown in this diagram in the yellow box are our ACPI tables, or DT, which the OS needs in order to be informed about these features and their respective parameters. The supervisor execution environment needn't be firmware. In the case the OS is running in a virtual machine, the SEE may be implemented by the hypervisor. Since the OS doesn't need to be concerned as to whether the SBI call takes it to HIM mode or HS mode, we'll only consider the former for this talk. Actually, as start in this diagram, we'll be focusing specifically on the hardware descriptions and the SBI calls. Even if a platform chooses to use DT for its hardware descriptions, it's useful to specify the types of power and performance states a system may be in at any given time. Looking at ACPI's categories can help us do that. ACPI defines global states as well as performance states and idle states. Global states affect the entire system, which recall may be a virtual machine, in which case it would not affect the entire real system. Performance and idle states are per heart. Hearts may be in different states unless they are members of the same cluster and the entire cluster is dictating a state. A note is that while older ACPI specifications addressed idle states with C states and performance states with P states, later versions have introduced LPI and CPPC, which are considered more flexible. So we focus on those in this talk. Also note, we also focus on system states, not device states, D states. The diagram shows the states and how they relate to each other. We'll go through each of these in the coming slides. This slide is to quickly introduce FFH, as we'll refer to it again in later slides. FFH allows the ACPI specification to be extended for specific families of platforms. It can be used for specifying physical addresses or function IDs and function parameters. For example, ARM has an FFH to further specify how to interpret ACPI's LPI and CPC objects. RISC-V is going to need something similar. Global states G0, G2, G3 are simply on and off. The system is powered on by supplying it power, but powering it off is usually software initiated, which is where SPI comes in. Power off SPI support is specified in the SRST extension, which is already ratified. Currently, no hardware descriptions are provided for the SRST extension because the existence of the extension is enough to imply the standard reset types that it supports. Those reset types are shutdown, cold reboot, and warm reboot. Linux has actually had support for SPI extension since 5.17. A system may be in a state of minimal power consumption when it has no work to do. That state is called a sleeping state. Multiple levels of sleep may be supported. ACPI defines 4, which are typically implemented as suspend idle, suspend RAM, a deeper suspend RAM, and hibernate. Most importantly, lower sleep states must have a shorter entry and or exit latency than higher sleep states, and higher sleep states must have equal or greater energy savings. SBI extension proposal for system suspend is in progress, and we've implemented a proof of concept. The approach is similar to ARM's PSCI system suspend, where a single sleep type is implemented, which is S2, S3, a suspend RAM type. No hardware description is currently necessary, as the existence of the SPI extension is enough to imply suspended RAM is supported. But It is possible to add more types to the SPI extension. So a hibernate type, for example, could be added. And then at that point, hardware descriptions may also be needed. Like sleep states, higher numbered low power idle states have higher entry and exit latencies, but also higher energy savings. Since an idle heart waits until an interrupt arrives, notifying it of more work to do, a natural choice for a low power state is simply to run WFI, and higher numbered states can then be WFI plus further cuts in power. The policies used to determine which state to transition to and for how long to stay in that state before transitioning further are implemented by governors. The OS can transition to different low power idle states using a function of the ratified HSM SPI extension, where the parameter corresponding to each low power idle state level, which is passed to the function, are discovered from ACPI tables, further interpreted per the FFH, or from the DT. Linux's CPU idle driver with DT has had support for low power idle states since 5.18. When a heart does have work to do, it doesn't always need to do the processing as fast as it can. When it can reduce its clock frequency, its voltage may also be reduced, substantially reducing its energy consumption. ACPI's CPPC specifies abstract performance thresholds, so the OS doesn't need to know platform-specific frequency voltage pairs, nor consider platform-specific details like power and thermal budgets. These abstract levels have names like highest, nominal, and lowest. While the OS can set the desired performance register to its requested level, the actual performance level delivered is determined by the platform. This means the OS needs to check what the actual level delivered is, but the instantaneous level is not all that interesting. It's best to get the effective level over a given time period. The effective delivered performance level can be calculated with the formula on this slide. Here, the reference performance is the performance level at which the reference performance counter accumulates, and it's used to scale the ratio of the number of delivered counts to the number of reference counts for the time period. The reference performance counter must count at a fixed rate, while the delivered performance counter counts at a rate proportional to the current performance level. To enable performance states for RISC-V, we described the CPPC registers in the ACPI tables with the CPC objects with the help of the FFH. The FFH can also indicate from where the OS should get its reference and delivered performance counters, either through SPI calls or directly from the time and cycle CSRs. Finally, the ACPI tables additionally describe how hearts are grouped into performance domains with PSD objects. This diagram shows an SPI configuration. The diagram includes the low-level firmware with a potential optimization of using per-heart channels to modify performance levels. And now we'll show some demos.
In this demo, we watch a YouTube video through SM Player running on a QEMU RISC-V machine. We then initiate a suspend to RAM, which synchronizes file systems, freezes tasks, stops non-boot hearts, and finally makes the system suspend SPI call. While the system is suspended, the video will freeze. When the system is resumed, it will start up where it left off. For this demo, the SPI implementation just waits 3 seconds and then initiates a resume. Let's see it again. After double checking that there weren't any failures, we're all done. On the right-hand side, you can see 3 ACPI LVI objects for each heart created by QEMU, where the first is always WFI and the other 2 are retentive and non-retentive idle states. Of course, platforms can add more LPI states if they like. Hearts enter different idle states based on the governor and the load. By default, Linux will boot with the menu governor, and you can see the ACPI idle driver is active. We can see that the residency and the latency are populated from the LPI objects. The usage counter shows how many times the heart entered an LPI state. The governor, along with the scheduler, determines the LPI state to enter. We can see a sample CPC object on the right-hand side created in QEMU. The desired performance register and the delivered and reference performance counters are FFH addresses. The nominal frequency is set to 100 MHz. Each policy represents the group of hearts in the same performance domain provided by the PSD method. In this sample, each heart is in its own domain so that its performance state can be modified independently of other hearts. Supported governors can be seen in the scaling available governors node. We can see the current CPU freak driver is CPPC. When Linux boots, it boots with the performance governor, which sets the heart frequency to the nominal frequency. We can see the maximum and minimum frequencies set by the governor, and also the current frequency. If we change the governor to power save, it reduces the heart frequency to the lowest possible to save power. If we change the governor to the user space governor, we can set the heart frequency by writing to scaling set limit. In this example, we set it to 80 MHz. If we set it to conservative, we can see that the frequency is gradually reduced.
In the demos, we saw functioning proof of concepts. This slide summarizes the overall status of the work. A system suspend SBI proposal has been drafted and is nearly ready to submit for review. The patches used for the proof of concept are also ready to submit. Since no hardware description is necessary for the proposal, the proof of concept works with both DT and ACPI systems already. Low power idle states already have a ratified SBI extension and code merged for use with DT. For ACPI, an FFH is needed and a draft is in progress. Patches are getting closer to being ready for submission. Performance state support has an SBI extension proposal in progress, and another chapter of the draft FFH being prepared for the low power idle states is needed. And proof of concept patches are also being polished. Thank you.